It was like six, like fuzzy one, but so kind of like really picking you can do with my family.
I get it. Yeah.
I'm not doing that program this year because I could like draw as like an interval. Probably do it just.
Even harder logarithms. Listen, I know that people don't often pay too much mind to the marble jars behind me, but there's now a full 19-day differential between days remaining and days completed. 19 on the good end, like we're headed towards golf season end. So it's getting there. It's happening quickly. Like I remember when we were 19 days on the other end of the equilibrium, and now we're, it's not technically 19 days. I mean, it's like 9.5 if you balance it out, but still that's pretty cool. So yeah, it's happening quickly. It's going to be summer before you know it. So yeah, these are not the kind of logs that we're going to try. It's even harder logarithms. I didn't know what else to write because yesterday's notes, I think, I called it evaluating harder logarithms, and these are a little bit step up even harder than those. So I just thought, if like, ooh, that cup of water is hot, ooh, that one's even hotter. I didn't know what else to put. So bless you. So you'll see right away kind of what I mean. So let me give you, if you don't want to write these ones down, I wouldn't blame you. The logarithms that you've been faced with to this point, you can do pretty much mentally if you know your basics. So again, I wouldn't probably write these down just because this is kind of what you already know. So for example, if I gave you like log base 2 of 1 over 32, assuming you've been present and been doing your work, you know that that's a -5, right? Because you need 2 to the 5th to make 32, but because it's happening on bottom, you would need to use a -5, right? That is, of course, assuming, like I said, that you've been doing the work to this point. So all the logs so far have been things that you could just look at the base and in your head probably figure out what exponent you need on the base to turn it into the argument. That's been there. I haven't given you a single problem yet that really requires a lot of work to do. There's been a little bit of maybe side work. So like yesterday, part of what we learned was like if I gave you log base 8 of the 5th root of 8 cubed. Again, there's maybe a little bit of side work, but you still can make a case for saying I can do this in my head. Like I know that the answer is just 3/5, right? So it's all been pretty routine and ho-hum. There was a little bit of even trickery yesterday where I gave you like a log base 2 of the cube root of 16. And even this, once you get good at it, you can do in your head. Our trick that we learned yesterday is I can take 16. Remember, we played Operation Match the Bases, right? And so like I could take this number 16, and what would I actually write the number 16 as? I would write it very purposely as 2 to the 4th, because when I'm playing Operation Match the Bases, I want this base here. I'll put a little green box around it to match this base here. And once match the bases is done, then the answer, I think, is obvious. It's just 4/3. So this is kind of where we've been at so far. That ought to be kind of water under the bridge. So what happens today is we don't have the luxury of just having the ability to just outright match the bases. We do, but it's a little bit more of a process. It's a little bit more of a roundabout process. So for example, I've got 8 examples. I can certainly conjure up some more. I didn't know how many you would need. So we have log base 81 of 27. There's always going to be the ability for people who are really mathematically solid to look at this and figure out, okay, you could mentally attack this, but it's not a road I want to go down. Like I don't want to be the adult who says that that's how we're going to do this. So I have an ironclad way for you to do this in any problem like this. And like I said about 5 minutes ago, if you're willing to really faithfully follow these steps, you'll have zero troubles at all. So here we go. You see the issue here is like I'm asking you this question. Don't write this part down, but I am asking you this question. 81 to what power equals 27? Like what? I can raise 81 to an exponent and have it equal 27. You can. And the question is, what is that exponent? It's definitely not a negative because I see why you would want to say that for the record, but it's not a negative because it doesn't become a fraction. So through mental math, you can manipulate it. You know what it is? It would not be. It wouldn't be 3 because, and it wouldn't be 4. Like think about the things you're saying. So like 81 to the third power, just let me give you some perspective on this. 81 to the third power is 531,441. I think the answer, it'll have to be a fraction because the only way to make this happen is to turn 81 down into 27. You have to shrink it. So there's going to be some rooting in there somewhere. So the answer, I think, is 3/4. But like, how do we come up with that? That's the question. And so let me show you the way we're going to attack these problems. And then if you want to get a little creative later on and start kind of trying to mentally do them, you're welcome to do that. And I can kind of show you how I tried to do that in my head too. But for now, this is the method that will always work. So step one in this process is to take your math problem. You're going to be doing these on paper for sure. And at the end of the math problem, you're going to put equals x. Because if you think about it, the answer is x, right? Like if it said like log base 2 of 8, we would write equals 3. So, I mean, same idea here. So by making this into an equation, we now have the ability to embrace the water cycle diagram. And this will become much more prevalent now. I made a reference to it about a week ago or so. But what we're going to do is we're going to embrace just the fundamental idea of what a logarithmic equation says. It says quite literally this: 81 to the power of x equals 27. And I would draw those arrows in my notes if I were you, because that's going to be the cycle, the relationship, the diagram that gets us through these problems, these harder problems like this. So as I start with the number that's circled and follow the little water cycle diagram, you know what I mean? Write the equation that happens as you follow the diagram. And it literally says 81 to the power of x equals 27. Now, we don't know some stuff about logarithms yet, but there's properties of logarithms that enable us to solve equations like this. That's for another week. For today, though, we do have the ability to solve this. And we're going to again play a game of Operation Match the Base. The trouble this time is there's not one base that I can turn into the other. Like I can't turn 81 directly into 27, and I can't turn 27 directly into 81. However, here's the big brain math question that kind of gets us through. If I put a yellow box around that and a yellow box around that, not the x, I'm only including the numbers. Those numbers are both powers of something. What is it? Yes, they are both powers of 3. I would say 9 if it weren't for that 27, but 9 to some power cannot equal 27, right? Like 9 to the first is 9, 9 squared is 81, 9 cubed is 729. But I do know for a fact that this gold box over here is 3 to the fourth. You know that too. You should by now, that 3 to the fourth is 81. You also know that this gold box is 3 to the third. So that's the game of Operation Match the Base. And so now what I'm going to do is I'm going to reapply that exponent, the x that I did not include in my gold box, and I'm going to stick it right here like this, and I have an equation now. Now, going all the way back to whenever it was that you learned basic properties of exponents, generally that happens in 8th grade, assuming you took 8th grade math. What happens is there's a little bit of a math problem right here. There's a property of exponents at play, and you've seen it this year too. What happens when you have a power and you raise it to another power? What do you do with the powers? You multiply them together. So what this equation says now is 3 to the power of 4x equals 3 to the power of 3. Are we okay to this point? So this is where we go big brain mode. It's like actually just common sense. But until you see it, you could stop at this part and say, this is where I get stuck. So listen along with me and say something if this doesn't make sense. If I take the number 3 and I raise it to the power of 4x, I get an answer. And then if Matthew takes this number 3 and he raises it to the power of 3, he gets an answer. But there's something really important in this problem, and it's right there. That equal sign is important because he says that the answer that you get on the left and the answer that you get on the right are the same. So if I raise the number 3 to some power, and then Gavin raises the number 3 to some power, and we get the same answer, you disagree with me if you want. You should if you disagree. If we get the same answer, then doesn't it have to be true that our exponents had to have been the same? Is there any way for me to raise 3 to the power of 4x and Gavin to raise 3 to the power of 3 and have us get two answers that are equal to each other with those powers not being the same? It's impossible. The only way to crack the code is to say, well, Gavin and I, it may not have looked like it, but we used the same exponent on the number 3. There's no way in hell we could get the same answer if we didn't use the same exponent. So if the exponents equal each other, then this little baby 6th grade equation over here is the answer to my issues. Divide both sides by 4, x equals 3/4, and we are done. If you find a shorter way to do this, feel free to do it that way. Make sure you show enough work so that I'm okay with it, okay? All right, thanks. How'd that feel? Scale of 1 to 10. 1 is like, no way. 10 is easy peasy. Let's practice again. 6, not bad. Let's go again. Log base 32 of 128. Again, you see the issue here is 32 cannot directly be raised to some easy power to turn it into 128. So there's a fraction witchcraft involved here. So what is step 1? Equal it to x. Very good. Step 2 is to go for the water cycle diagram, and I'll draw this a lot. Try to do something enough times in hopes that kids say things like, maybe I should do that too. So I'm going to say this to the this equals this. And I'm going to write that out. The result of that diagram is what is going to come out as an equation. I'm going to write 32 to the power of x equals 128. Now you got to know stuff. I mean, there's no way you can follow steps, but at some point you got to face it and say, I got to know some basic skills here. Bless you. What are 32 and 128 both powers of?
2.
They are. They're both powers of 2. So I can take the number 32 and write it as what? Yes. And I can take the number 128 and write it as what? Yes. 2 to the 7th. Got it? So when you slap that x down here onto the 5, 2 to the 5x, again, the logic is simple. Exponent on the left has to equal the exponent on the right. So 5x has to equal 7. So x has to equal 7 divided by 5. Done. And you do enough of these, and I'm telling you, even without me showing you, you can actually get to a point where you can look at these and do them in your head. It is possible. You might already see it. I don't know. And let's go again. Log base 243 of 81. Step 1. Step 2. Do the cycle. 243 raised to the power of x equals 81. So 243 raised to the x equals 81. What are 243 and 81 both powers of? They are both powers of 3. So 243 is 3 to the 5th, and 81 is 3 to the 4th. 5x has to equal 4, x equals 4/5. Now I have one more example before we get to the fraction ones. The trying to make fraction ones. And I just wanted to throw this in here because, I have a tendency to sometimes leave things out. So you will see problems that are much simpler to do in your head like this. There's nothing wrong with you if you can't do this in your head. But if you look at this, it's a much simpler example because there's a way, if you're clever, to very directly turn 27 into 3. You're not allowed to say divide by 9. Of course, that's not the game we're playing here. How can you turn 27 into a 3? You could cube root it, couldn't you? So if you're really savvy and a problem like this comes up, you could just jump right in, say, I already know the answer is 1/3. Because if I take the 27 and raise it to the power of 1/3, that's really the same as saying I'm going to cube root u27, and I know the cube root of 27 is 3. But let me show you what this looks like if you're not feeling that, like if that's not what you want to do. So if I follow my own steps, set it equal to x, and then embrace the cycle, the equation is going to say 27 to the power of x equals 3. 27 and 3 are both powers of what? 3. So the one on the left becomes 3 to the third. Stick the x on there. And the one on the right is 3 to the first, right? And so it's going to all come out. Like you can follow, I wouldn't lie to you about this. Like you can follow these steps and it's just going to keep working. But there will be problems where you start to kind of get in a groove and go, I could have done that quicker, right? If I see a root that can be just applied, boom, massive direct root, take it. So like in this one, if 3x equals 1, then of course x equals, like we said, 1/3. So another example of that could be something simple. Sorry if you were still writing, I'll scroll back a little bit. So if I gave you like log base 64 of 8, super direct approach. How does 64 become 8? Yeah, by square rooting it. And another way to square root is to raise something to the 1/2 power. So shorter problems do exist. Good so far? Okay. So the other side of this coin is where the argument is a fraction. So if I have, say, for example, log base 4 of 1 over 128, we know right away our answer is going to be a negative. We talked about that yesterday, that in order to get the argument, to make the argument of a fraction, you have to use a negative logarithm, right? So let's follow the exact same steps. Set it equal to x. A little bit trickier this time if you're a little bit kind of weak in the basics here, but we still embrace the water cycle diagram. So we're just going to say 4 to the x equals the fraction. So the equation looks like this: 4 to the x equals 1 over 128. So don't be taken aback or freaked out by the fraction, but just focus on the number parts themselves. What are 4 and 128 both powers of? So I'm going to take the 4 in this gold box, and I'm going to write it as 2 squared. And then I'm going to attach the x, because that's the x side, right? Now, what power of 2 do you need to make 1 over 128? Yes. So this side is 2 to the negative 7th. You know 2 to the 7th is 128. To get it to be 1 over 128, you just need to make the power a negative, right? And once again, what pops out is a very basic equation, right? If 2 to something equals 2 to the something else, then the something and the something else quite literally have to equal each other. So exponent on the left must equal exponent on the right. X must equal negative 7/2. Okay. Still good? just like the last section of notes, these first three are not going to have a direct route. 9 doesn't directly, using pleasant numbers, just turn into 243. But embrace your cycle, set it equal to x. The equation would say 9 to the x equals 1 over 243. Uh-huh.
Could you just ignore?
Yes. Yes. If you want to ignore it as a fraction and just solve the problem as if it were a 243, yes, that will become more difficult, Brady, when we get to harder problems where the top number is not a 1. But for now, since it's 1 over, all of today's will be 1 over, you could get away with that for now. I didn't mean to cut you off, but I assume you were going to ask, can we ignore the fraction and then just make it negative? Yeah, of course. But I don't teach it that way because it's not going to work for long. Okay? But for today, yeah, totally. So 9 and 243 are both powers of what? Definitely 3. So 9 is 3 squared. Stick the x on that side. What is 243? Right. We need it to be -5. So this side is 3 to the -5. And then again, like Gavin pointed out earlier, from this point, if you just look at the exponents that you have, you're welcome to just, here's what'll get you in trouble. This is when I get cranky pants, is if someone looks at these and says, oh, I got it, homie. The answer is -2/5. Like that's going to get you in some big heat with this guy, right? So just be aware of what's dividing by what. So when you look at those exponents, you see that it's the -5 that winds up getting divided by the 2. So x is actually -5 over 2. Don't do anything criminally stupid like divide by the wrong thing. Okay. Here's one that has a direct route. Log base 125 of 1/5. So you start to just get smart about this and say, sometimes I don't have to go through all of this. So like Brady said, if I just ignore the fact that it's even a fraction, if I just take a direct route, how does 125 turn into 5? By cube rooting it. But since it's a fraction, it has to be a negative. And since it's a root, it has to be a fraction. So if I wanted to do this quickly in my head, what would the answer be? It has to be negative and it has to be 1/3. It's negative to get the flip and it's 1/3 to make the root, right? As before, though, I don't want you to feel left out right now like that made no sense. So let's go back to our standby, set it equal to x and do the process. So we write 125 raised to the power of x equals 1 over 5. You see that the number parts on the left and the right are both powers of course, 5. So 125 is 5 to the 3rd. Slap the x on there. 1/5 is 5 to the -1st. Exponent equals exponent. 3x equals -1. X equals -1/3.